Okay, so section 5.4 is starting on page 63 of your course notes, and this is using what we've learned about critical points, inflection points, concavity, slope to graph a function. So on page 63, it goes through the steps of curve sketching. So basically sketching the graph. So we want to follow the steps, and some of them we will be able to skip at different points depending on the function. So first we want to find the domain. So we want to look for asymptotes as well, okay? So something that's not in the domain, like something that would make us divide by 0, would be a vertical asymptote, okay? Find the y-intercept and find x-intercepts. If they're not too hard to find, sometimes they can be really difficult and it's not worth it. Okay, if the function is rational, meaning it's a fraction, find any vertical and horizontal asymptotes. If the function is exponential, find any horizontal asymptotes. If the function is logarithmic, find vertical asymptotes. So this step 3 could be summed up as find asymptotes. Step number 4, find the derivative, locate any critical points, any relative max, and determine where the function is increasing or decreasing. Okay, then we want to find the second derivative, find inflection points, so we can see where it's concave up or concave down. And then we're going to kind of plot all of that information that we found. Okay, all right. So, first example, sketch the graph of f of x equals 2x cubed minus 3x squared plus 1 using the steps listed on the previous slide, so on page 63. So the first thing you want to find is the domain. So step number 1, our domain, there's no restrictions for this one. There's no denominators, there's no radicals, so our domain is -infinity to infinity. Easy enough. Now we want to find x and y intercepts. That's step number 2, if they exist. So remember, to find a y-intercept is when x is 0. To find an x-intercept is when the opposite, y is 0. And again, this is just our regular function, basic, okay? So if x is 0, plug in 0, we would get 1, okay? So we have a intercept at 1, 0. If we plug 0 in for y, we have 0 equals 2x cubed minus 3x squared plus 1. Now, this is not necessarily easy to find, so I'm going to put ... Again, our instructions said if it's not difficult to find, we can definitely graph this pretty well without x-intercept, so let's leave that part. Okay, and then step 3, we want to find asymptotes. So if it's rational, find vertical and horizontal asymptotes. This is not a rational function. There's no denominator, so we don't have to deal with that, right? So if we had something that like x plus 1 in the denominator, we would have vertical asymptote at x equals -1. If we had exponential or logarithmic functions, we'd have to worry about that. But this situation, we don't. It's just a polynomial, so no asymptotes. Okay, so step 4 says to find the derivative and locate critical points, relative extrema, and determine where the function is increasing and decreasing. Okay, so the first derivative would be 6x squared minus 6x. Okay, okay, so we want to set this equal to 0. We could factor out a 6x from each of these, be left with x minus 1. So we would get x equals 0 and x equals 1. Okay, so if we continue number 4 on a number line, we plot 0 and 1. We want to check the derivative at each of anything less than this. So we could plug in -1 to the left of 0. If we plug in a -1, we will get a positive output. Okay, so we're positive in this region. If we plug in something between 0 and 1, so say 1/2, we would get a negative value. And then if we plug in something greater than 1, say 2, we would go back to positive again. Okay? So that means, I guess we probably want, yeah. So this would mean that our slope is increasing. Remember, this is our first derivative. Our slope is decreasing and our slope is increasing again. So we want to actually know what these critical points are, right? So if we go back over here at x equals 0, we want to know what y value is in the original. So we actually have, that's a relative maximum, and then at 1 we have a relative minimum. So we want to know what those points are so we can actually plot them on a graph. Okay, so to save time, you can plug it in. If you plug 0 into the original function, we just get 1. Fortunately, these are pretty easy to plug in. If we plug 1 in, we get 0. So again, 0, 1 is a relative maximum, and the point 1, 0 is a relative minimum. Okay, so that's step 4. Kind of a long step. Okay, find the second derivative and locate any inflection. So we have a y-intercept at 1, 0. Okay, have a relative maximum we know are at 0, 1. So that's our intercept, and at 1, 0. We can also look at our slope. We have a positive slope from 0 to 1. From -infinity to 0. Okay, so our second derivative then would be 12x minus 6. We want to set that equal to 0. So we would get x equals 1/2. So we want to check values on either side of this. We could check 0. We could check 1. If we plug 0 in, we would get a negative number, right? Which means it's concave down. And if we plug in 1, we get a positive number, which means it's concave up. Okay, so then the next step. Oh, and we want to know our inflection point. So if we plug in 1/2 into our original function again, okay, the actual points on our graph, we always want to find in the original function, okay, not in the first or second derivative, because that wouldn't be plotting the original function. So if we plug in 1/2, we get 1/2. Okay, now this, we'll check my skills here of graphing. So we have x and we have y. We want to look back at all these points we've found. Now we're using some halves and stuff going on, so this is not going to be perfect. Let's just do as good as we can. So -1, -2, there's our halves. -1, -2. And we have some halfway marks. Oh, my scale is not quite right, as you can see, but I'll give us the general idea of what this graph looks like. Okay, so we said our y-intercept is 0, 1. So that would be a point here. Okay. Okay. Now, we also know our concavity is changing at 0.5 and 0.5. So right here, our concavity is changing. Now, we also know it's concave down from -infinity to 1/2, and it's concave up from 1/2 to infinity, 0, right? So we're increasing, and then we have a negative slope and then a positive slope. Okay, now we can check kind of to see if we knew x-intercepts, that would help, but we can kind of have a general idea that this is what our graph is going to look like from the values given. Okay, now how fast it's curving, we don't know exactly, but we do know where the general curves are. This is kind of an ugly curve. Let me fix this a little bit. Okay. So again, we're looking for generalizations. We don't need an exact graph. We have computers for that, but we want to understand the dynamics of what is happening to our graph. Now, often, because this is in my math lab, often you will not be asked, you can't actually graph it on the computer, so you will be given multiple choice answers. And from the information you find about the graph, you can use process of elimination. So check inflection points, check relative max, relative min, check where the slope is, where it's concave up and concave down. It'll be a little quicker than actually trying to graph it. I would encourage you, though, in your homework to graph it on your paper. And get the hang of it a little bit. It will really help these facts to sink in and help you remember them. Okay, example 2. Sketch the graph f of x equals x to the 4th minus 4x cubed plus 10. Okay, again, this is a polynomial, so there's no restrictions on our domain. So for step 1, our domain is negative infinity to infinity. Okay. We want to find x and y intercepts if we can. Notice again, x-intercept is going to be challenging to find, but we can find the y-intercept. If we plug 0 in for x, we get 10. So our y-intercept is 0, 10. Quite easy. This is a polynomial, so there are no asymptotes, luckily. Okay. And then for the next one, we want to find critical numbers and where the slope is changing. So we find our first derivative would be 4x cubed minus 12x squared. We want to set this equal to 0. So we can factor out a 4x squared. We'd be left with x minus 3. So we get x equals 0 and x equals 3. Okay, so now we look at the number line. And we want to check whether our slope is positive or negative. So we're plugging values in between these into our first derivative. So I'm going to give the answers for the sake of time. We have negative slopes between negative infinity and 0 and 3. So those are not critical points. And then we do have a critical point at 3. If we plug 3 into the original function, we get the y value of negative 17. So this is a critical point. Notice we have a negative slope and then a positive slope. So it is a relative minimum, and we can verify that with the second derivative. Okay, so that is step 4. Step 5 says to find any inflection points and determine concavity. So our second derivative would be 12x squared minus 24x. We want to set this equal to 0. So we can factor out a 12x from each of these. We get x equals 0 and x equals 2. And if we plug in values here into the second derivative, remember, we get positive, negative, positive. So that means we're concave up, we're concave down, and then we're concave up again. Now, when we find our inflection points again, those are found by plugging these values into the original function. We get 0, 10, and 2, negative 6. Okay. So let's try to graph this. First derivative from negative infinity to 3, and then a positive slope from 3 to infinity, okay? But our concavity is changing twice, okay? So what the graph is going to... Okay, there are no domain restrictions, so there are no vertical, horizontal, or oblique asymptotes. So we want to... let's see, we want to determine a scale for this. Notice our inflection points are high on the x-axis, or on the y-axis, excuse me. We have 10. We have a critical point at 3, negative 17, but our x-axis is relatively small. So let's do it this way. 1, oops, I got an eraser. 1, 2, 3, 4. Same thing to the negative. One thing I will say on my math lab be very careful to look at the scale of the graphs because sometimes they are different. So let's go 5, 10, 15, and -5, -10, -15. Okay, so plotting our points. We have a critical point at 3, -17. So that would be down at x equals 3, y equals -17. There-ish. We have an inflection point at 0, 10. Remember, that's where it's changing concavity. And our y-intercept is also 0, 10. We didn't find our x-intercepts, but if we did, they're in between 1 and 2 and 3 and 4. Okay, now notice we have a negative slope, right? If we end up looking like, because 10 is an inflection point, is we have a negative slope and we're going down, but it's concave facing up. I don't know if my graph here, it's probably more like a little more dramatic looking so you can see it. Concave up, right? And then it switches to concave down, but still has a negative slope. And then we hit 3, -17, and we're switching slope. So at x equals 3, we're switching slope. And we also had an inflection point, let's see, at 2, -6. This was an inflection point. So we're switching from concave down to concave up. I should have graphed that before. Okay, so that's our general graph function. Okay, note, if there's any asymptotes, we want to start by sketching those, just following the steps, and that gives us a very good framework for the rest. Okay. Step 1, we want to find the domain. So we cannot divide by 0, so we'd have -infinity to 2 and 2 to infinity, right? Note x cannot equal 2, but that's our only domain restriction. Okay. To find our x and y intercept, plug in 0 for x, we would get 0, right? So our intercepts are both the same in this case, 0, 0. Okay. Now, we actually have 2 asymptotes. Okay. We have asymptote at x equals 2 because we cannot divide by 0. And then because the degree, you can review this later on your own time. I'm sure there's lots of YouTube, but to find vertical asymptotes, if the degree of the numerator and denominator are the same, we have y equals the leading coefficient, so 3 divided by 1 or 3. If the denominator degree is greater, we have a y-intercept of 0. If the denominator degree is greater for a rational function, then we have the horizontal asymptote y equals 0. And if our numerator degree is greater, then we have an oblique asymptote, and we use synthetic division or long division to find it, ignoring the remainder. Okay, so you might have to review that. Okay. Step 4 is to find critical points. So we find the derivative. A little bit more work in this case. We have a quotient. So we take the derivative of the numerator times the denominator times minus numerator times derivative of the denominator, which is just 1, divided by denominator squared. And then we want to set this, we can simplify. We will end up with -6 over x minus 2 squared, and we want to set this equal to 0. Okay, but this can't happen, right? There's no solution, so there are no critical points. Okay. Now, if we look, we do have a hole at x equals 2. So if we're looking at our number line, they're both negative. So our function is always decreasing. Okay, our slope is always negative. At x equals 2 and a horizontal asymptote. Okay, so that gives us an idea of what it looks like. Now, 5th step, we find our second derivative. And I'm going to do that real quick. Try to cut down time here. We have 12 over x minus 2 cubed. Again, this will never equal to 0, so there are no inflection points. However, we do want to look, always you want to look at where your graph does not exist, so where they're, like in our original introduction of inflection points. So we're going to check 2, and we get negative values and positive. So that means our concavity is changing. Even though our slope is always negative, the concavity is changing. So we're concave down from negative infinity to 2, and concave up from 2 to infinity. Okay. So we have a vertical asymptote at y equals 3. And we're going to draw a very general sketch. We have an intercept at 0, 0, though. We do know that. We could always just plug in points into our original function and plot them. So we could plug in anything, really, right? And we could plot those points. But if we do that, we will get a graph that looks something. We know it's here. We know it's concave down up to 2. And then it's concave up. And it is going to end up looking like this. Again, you can plot lots of points in the original function and figure out until you get the general idea of where the graph is. And then if this is a My Math Lab question, then you're going to be just picking multiple choice. Okay, last example on page, where are we at? Page 66 of your course notes. It gives us a list of criteria and asks us to graph this, okay? Okay, so let's start now. Because I've done this before, I know it goes, all the values here, and you can look at the values on the list are fairly small, so we don't need we don't need a huge scale, but we do have some asymptotes. We have a horizontal asymptote at y equals 2. We're going to graph those first. And we have a, what does it say? It has a vertical asymptote at x equals negative 2. Okay. Now, it says f, the derivative of x is less than 0 everywhere it is defined. So that means a negative slope everywhere. Okay, a horizontal asymptote, our derivative, our second derivative is less than 0 from negative infinity to negative 2 and from 0 to 2, right? So that means it's concave down from negative infinity to negative 2 and from 0 to 2, okay? And then it says our second derivative is greater than 0, so that's concave up from negative 2 to 0 and from 2 to infinity. Okay, so there's no maxima or minima values given to us, right? Because the derivative is negative everywhere. And then we have concave down from negative infinity to negative 2. So let's look at that first. So we're concave down here. And then we are, let's see, concave down also from 0 to 2, and it's concave up from negative 2 to 0. So our graph looks like something like this, and then it goes concave down, and then it goes concave up. Okay, so that's kind of a guess. Again, this is not going to be exact, and in My Math Lab, you're going to be using a process of elimination to figure this out.